Hi, this is Alex from devstories.eu. LangGraph, episode 15 of 18. When your AI agent grows complex, you often end up with one massive, unreadable megagraph where a single change breaks everything. You do not have to build that way. You can build specialized mini-graphs and snap them together instead. We are talking about composing complexity, subgraphs. Subgraphs let you reuse logic and distribute development across different teams. Instead of putting every single step of your application into one file, you create smaller, self-contained graphs. Once a graph is compiled, it behaves exactly like a standard callable function. That means you can take an entire compiled graph and drop it directly into another graph as a single node. Think of a master routing system for an enterprise assistant. The main graph handles user input, checks security, and decides what to do next. When a user asks a deep technical question, the router needs to perform complex data gathering. Instead of coding that logic directly into the router, you delegate it to a dedicated research subgraph. A completely different engineering team can build, test, and refine this research graph in isolation. The parent graph does not care how the research is done, it just calls the node. There is a common tendency to overcomplicate how data passes between these graphs. If the parent graph and the subgraph use the exact same state schema, meaning they share the exact same state keys, you do not need any special adapters. You simply pass the compiled research subgraph directly into the add node function of your master graph. The engine automatically feeds the parent state into the subgraph, runs the logic, and merges the results back into the parent state when it finishes. Now, what happens when the teams do not coordinate perfectly? Suppose your parent router uses a state key called user query, but the separate engineering team built the research subgraph to expect a key called search term. You cannot drop the compiled subgraph directly into the parent graph. The keys will not match and the execution will fail. Here's the key insight. You bridge this mismatch using a simple wrapper function. In your parent graph, you define a standard node function that accepts the parent state. Inside this function, you extract the user query value. You then call the compiled research subgraph manually, passing it a payload where you map that user query to the search term key. The subgraph runs its internal logic and returns its final state. Your wrapper function takes that output, translates the results back into the specific keys the parent expects, and returns them. To the parent graph, this wrapper looks like any normal node. It has no idea a massive, complex subgraph just executed inside it. It simply passed data in and got updated state back out. This pattern gives you strict modularity without sacrificing control. Treating a compiled graph as just another callable function behind a simple wrapper is the single most powerful way to scale an AI architecture without collapsing under your own code. That's all for this one. Thanks for listening and keep building.